How do magnets work? It's a pretty weird question when you think about it. I mean, we've all had some exposure to these things and have a basic idea of their principles. There are two poles, north and south, and like poles repel while its opposites attract. And they can also pick up certain metals such as iron, but not other metals such as aluminum. And have you ever stopped to ask yourself, why? There are so many simple questions about these remarkable objects which we just don't ask. Why do opposite poles attract? Why do they pick up only certain metals? What causes these deceivingly simple objects to have such bizarre properties? Well, today I intend to add you to the minority of people who can actually answer these questions. So let's get started. Now, a magnet is, by definition, anything which emits a magnetic field. Now, we can visualize these magnetic fields using lines of force, which we call field lines. And on a magnet like this, they would go from the North Pole to the South Pole, getting broader and broader in their paths as they get closer and closer to each pole. But what if we had two magnets? Now, in this example up here, a North Pole and a South Pole are meeting, and what this means is that the field lines from the North Pole are going to be coming into this South Pole instead of its own. So they're going to attract each other and come together, whereas here the field lines are going to be going up against each other and pushing, ergo creating a repelling force. Imagine if you had two beach balls and you pushed them together. It's a lot like that. Having explained that, let's talk atomic. Now, electrons, the tiny particles which orbit an atom's nucleus, not only revolve, but also spin, kind of like how the Earth does not only revolve around the sun, but also spins on its axis. Now, these electrons always come in pairs, one spinning in one direction and the other spinning in the other direction. Now, what's important to understand is the spinning of each electron generates a magnetic field, a tiny one, but a magnetic field nonetheless. But since they spin in opposite directions, they cancel each other out, and therefore it is a null field. However, ferrous metals, such as iron, cobalt, and nickel, have several unpaired electrons, meaning that their magnetic fields will not be cancelled out, making the entire atom ferromagnetic, which is what we think of when we hear the word magnetic. And when one of these atoms are spinning in a certain direction, and another atom comes along, then they both will be encouraged to spin in the same direction. And when this happens enough times, then we have the entire metal. Almost. You see, these metals form as crystals, which are separated into various domains, and each of these domains is magnetically oriented in a different way. For instance, this one's this way, and this one this way. And so they create just a kind of jumble of different fields which result in no field at all. This is called demagnetized metal. The easiest way to align these domains and therefore magnetize the metal is by using another magnet. So therefore we use magnets to make magnets. So to answer our original questions, why do magnets attract and repel? Intersecting lines of force. Why do magnets pick up metals? Disorganized domains. And why are things magnetic in the first place? Electrons spin. That's all the time I have for today, but before I go, I'd like to talk a little about my school, Laces Magnet, and why I feel it deserves this prize. Laces has a bit of a reputation here in Los Angeles. It's won every Science Bowl for the last 5 years, and it has the highest API of any secondary school Los Angeles has ever seen. However, Laces has been facing some troubled times for the last few years. This kind of record is hard to maintain, and our budget keeps getting dropped lower and lower by LAUSD, which is why a reward like this would be so useful to us. So please, consider voting for the Los Angeles Center for Rich Studies for this contest. Thank you for your time.